In this section of the textbook, we're going to look at quantum numbers. There are 4 different quantum numbers that I tend to think of as being an address for an electron. What we're actually doing is predicting the probability of where you're likely to find an electron inside an atom. So the 4 quantum numbers are the principal quantum number, and that's simply the distance away from the nucleus. The larger the principal quantum number, the further away from the nucleus it is. The angular, which is going to tell you the shape. So this is, we just saw in the last video, this is a p orbital, and so it's got an L value of 1. This is a s orbital, and it has an L value of 0, and we'll talk about how to know that. The magnetic quantum number is the orientation in space. You see this on this last video, or here, the fact that this one has 3 possible orientations in space. This one has 5 different orientations in space. And being a sphere, it doesn't matter which way I hold it, it still looks the same. And then the last one is the spin quantum number, and that's just going to be whether it's spinning clockwise or counterclockwise. Okay? So we're going to start with the principal quantum number, and as I said before, it basically is the distance away from the atomic nucleus. It's a positive integer, and an integer just means a whole number. So 1, 2, 3, 4, etc. And so this shows a 1s. This shows a 1s here, and then I have a 2s outside of this. Or if I look at it as a cutaway, the center here is the 1, and this outer part is the 2. Okay, I'm sorry, this is the 2 here. Okay, and so you'll see that it's easier to see on this one, but you can see it on both of them. So the darker the color, the higher the probability of finding the electron. So here you see the fact that it is a darker color here in the center, but you see this white line. Okay, so this white line separates the fact that these 2 electron layers do not mix per se. Under normal circumstances. Okay, we talked about you can promote an electron from a higher level to a lower level, but under normal circumstances, without any energy interjection, there's no electrons that are going to reside in this level. So we talked about them having different levels. Here's one energy level. Here's a different energy level. So this is when n equal 2 when we were doing the the Rydberg equation. Okay. So the angular momentum, like I said, gives the shape. Okay, so it's symbolized by the letter L. Okay, L starts at 0 and goes up to n minus 1. So what does that mean? Okay, so we're going to do problems on the next slide. Okay, but if you have to be told if I have an n equal to 5, that means that L could be 0, 1, 2, 3, and 4, because 5 minus 1 is equal to that 4. So it's going to have multiple values. It's going to be 0, 1, 2, 3, all the way up to whatever n minus 5 is. This is also this is where you're going to come into the electron configuration. So if you've seen electron configuration, these are the letters that are used here. And so those electron configurations represent the shape of the shape of the orbitals. So 0 is the spherical. The 1 is P, and it's the dumbbells. The D is the L equal 2, and those were the 5 shapes there. F is kind of too complicated to draw, and G is only in theory. It doesn't actually exist yet in reality. So as I said here, what are the possible, given the N and L values, give the N and L values for this. Okay, so N is always going to be the number here. Okay, so these 2 things are equal right there. Okay, and you'll have to remember, it's not going to be given to you, that S is 0, P is 1, D is 2, and F is 3. So you need to know this order here. Okay, so again, this is S, so oops, I did finish this one. So my L with the S here is equal to 0. This is L's here. All right, so for this one, N is equal to 3 because this number is 3. And then L is equal to 0 because of this number here. All right, on this one, N is equal to 2 because it says so. I'm going to switch to a different color so you can see here. The P ends up being here. So my L is equal to 1 because of the fact that it's P. Okay. I have 4, so n is equal to 4. So n's very simple. Okay, and when I have d, that means my L is equal to 2. And lastly, n for this one is 5. And L is equal to 3. Okay, so you do need to know this order. Okay, if you've done electron configurations in high school chemistry, this is the order that you fill them: S, P, D, and F. Otherwise, you need to learn them. They're really not in any order that makes sense. And then you just simply start counting at 0 and go up from there. The third one is the magnetic quantum number. And like I said, that's the orientation in space. It's from minus L to positive L. Okay, so S, like I said, is a sphere. Okay, think about a basketball. Basketball is also a sphere. It doesn't matter which way I hold that, it looks the same. So therefore, there's only one orientation. Okay. For the dumbbells, okay, then there's 3 orientations. There's the X, there's the Z, and there's the Y. Okay, so P has 3 orientations. Here's the D's, okay, they have 5. So we've already seen these 3 here, okay. And here's the representation of the F's, okay. And you don't need to know what these shapes are per se, just know that the fact that there's 7. So there's 1 here, there's 3 here, there's 5 there, and there's 7 of those. And so they go up in odd numbers by 2, okay. And so if I have an n equal 1, and therefore my L can only be 0, then M sub L would only be 0. Versus if I chose to do n is equal to 4, L could be 0, 1, 2, 3. Okay. If I chose 2, okay, then M sub L could be minus 2, minus 1, 0, 1, and 2. So that's the minus L to L. All right. So this is showing a table with a lot of numbers. Okay. So when n is equal to 1, because L can only be n minus 1, it can only be 0. Because L is 0, there's only one value for M sub L, which is 0, and so it has only one orientation of S, 1s. When n is equal to 2, I can have L equals 0 or L equal 1. For when L is equal to 0, M sub L can only be 0, and that's a 2s. When L is equal to 1, this is still 2 here, it can be minus 1, 0, and 1. So there's 3 orientations. So you notice that if I count these numbers 1, 2, 3, that's going to end up here. If I count this number, it's only 1. That's what counts up here. So this would be when n is equal to 1. There's only one possible orientation. When L is equal to 2, n is equal to 2, there's 2 possible ones. And when I go to n equal 3, there's 3 possibilities. See a trend here? So it can be 0, and therefore M sub L can only be 0. So whenever L is 0, there's only one possible M sub L value. When L is equal to 1, there's only ever 3 possibilities for this, and so that's where the 3 comes through. Minus 1, 0, 1. So from a minus L, which is a minus 1, 0 to a positive L. That's what you got there. When I go to 2, now all of a sudden I have 5 orientations. I have minus 2, minus 1, 0, 1, and 2. And this is a 3D because the D means 2. That comes there. And there's 5 orientations in space. 1, 2, 3, 4, 5. And the last one, which I don't have good color for, I guess we'll go purple. When n is equal to 4, and they do have larger n's, but we run out of L values, real L values. So you have the L values, that could still be 0, 1, 2, 3. That's what I had over here. Okay, my N was equal to 4, and I had the 4 possible L values. I chose L is equal to 2 and came up with those M sub L values. So again, L can be 0, 1, 2. These are the same as these 1, 2, and 3s for the M sub L's. I added 3, and now there's 1, 2, 3, 4, 5, 6, 7 orientations in space. So again, that goes back to S only having 1 orientation space, P having 3 orientations in space, D having 5 orientations in space, and the F's having 7 orientations in space. Okay. And the last one is the spin. There's only 2 possible ones, plus 1/2 and minus 1/2. So those are the 4 quantum numbers. And I'll come back with some problems on this in the next video.